Okay, so before we get started, let's talk about the homework. Questions 3 and 4, I think it was. For those of you who tried to do the homework, who could not get those two without like entering in the correct answer that I gave you?
Did not?
Yeah, so you could not, okay. This was kind of tricky. So I gave you like the correlation coefficient, I believe. You found the third one, but not the fourth. So does anyone have, can you open the page so you could read me the question in a minute? Because I forget exactly what the difference between the third and the fourth one were. I think they had to do with the slopes and the intercepts. Anyway, so we have this formula, at least for doing the simple linear regression. The simple linear regression is when you just have one independent variable. And we said that the slope, look at that, it's so beautiful. The slope is equal to the correlation, or R, times the standard deviation of our dependent variable divided by the standard deviation of our independent variable, right? It's like that. So now I said that you had these like z-scores that you were working with, right? As opposed to just regular old scores. And I gave you this piece of information. I gave you the correlation. So in order to figure out the slope, you needed to use this, which I gave you, and these, which I did not. However, if you know about z-scores, my goodness, it's cold. You should know what those things are. So yes, for z-scores, what we do is we divide every score by its standard deviation. And we use the biased estimate of the standard deviation when we're computing the z-scores. And by doing this, what happens? Well, since we're dividing every score by the standard deviation, then the standard deviation of that new standardized set of scores will be 1. Also, what else will happen? The means will be the same for both. And what will the means for both be? What is the mean of a set of z-scores? 0. That's exactly right. So for the first question, which asks you to do this, it's just R times 1 over 1. That's just R. So you just needed to put in exactly what I gave you, and you got the right answer. Now the next part, we need to solve for the intercept. And we said that the intercept was equal to the mean of our dv minus the mean of our independent variable times the slope. Well, what was the mean of the dependent variable in the z-scores? So we have 0 minus 0 times whatever this was. But 0 times whatever that is just 0. So the intercept is 0. So it really wasn't that hard if you thought about what z-scores are and how they're distributed. You have the information. I just didn't make it obvious because I wanted you to. Hopefully some of you guys got that. Okay. So let's talk about multiple regression and correlation. So let's start with some review. We have a formula for a line, y equals mx plus b. This is the form for a line that I learned when I was in high school. This is the form for a line that I used when I was in college as an undergraduate. So I'm very used to the y equals mx plus b. This formula, however, is not how it's typically represented in statistics. So in statistics, they use slightly different notation. And if you look through the sources on the study guide, or especially if you started Googling things, you would have found other variations of this that might have looked something like this. So y, our estimate of y, is equal to this b, which is actually equivalent to the slope. Yes. Get like 3 minutes of good use out of that. So this is equivalent to the slope. And this a over here, this is the intercept. Depending on what sources you find, you may find some other different types of notation too. But really the important thing is that one of these is a slope and the other thing is the intercept. The value that you see multiplying some other value, that's the one that's a slope. The other one's the intercept. Okay, so this is how things are typically represented in statistics. Our y with our hat, this is our estimate of y. This byx, this is the slope, which has a special name, a regression coefficient. Remember when we first started talking about correlations, we said that we have a correlation coefficient? And the correlation coefficient was what? It was just R. R was the correlation coefficient. Now this is a bit different. We use correlation in order to do regression. But with regression now, what we have is a regression coefficient. So if you are reading, you see regression coefficient, that's just a slope. So don't get confused. So it's the slope that we are using to estimate y from x, according to a linear relationship. And this ayx is the regression constant. Right? We have something that is affecting our values by multiplying with x. That's the coefficient. And the constant, that's the intercept. I'm sorry, this should not be slope. This should be intercept. Okay? So really no big deal. All right. Last class we talked about that we could express each value that we observed for whatever our dependent variable was as our estimate for that variable plus some error, right? So this y hat, that's our estimate plus error. So that's fairly familiar. So each score is just what you predict plus some error, and we can rewrite this. So we had a formula for our predicted scores on the previous page. So we can rewrite this as well. So we can say y, the scores that we actually observed, not our predictions, but the scores that we actually observed are the predicted scores, that's this, right? The slope times the actual x scores that we observed, plus the intercept, plus some error. No big deal. Now what if I have multiple independent variables? So that's the equation that we have when we have a single independent variable. What if I have multiple ones?
x1 and x2.
x1 and x2. So y equals, so this we could just say that that was x1, right?
And the second one will be just
So b
x1.
x1 plus
B y x2
y x2
and
x2
yeah, x3 plus
what?
intercept
Plus the intercept
and
plus some error. Sorry, e or error. So we can have something like that. Yeah. We have multiple independent variables. We're going to have a lot of things. We're going to have multiple correlations. We might not just have test 1 scores correlating with test 2 scores, but we could have test 1 scores also correlating with homework scores, and test 1 scores correlating with submission scores, and submission scores correlating with homework scores. You could have lots and lots of different correlations, right? You can have multiple correlation coefficients. You could have multiple regression coefficients, or the slopes. You only have one regression constant. You're going to find all the slopes, then you're going to make the prediction using those slopes, and using the mean x value. The means of your independent variables. Subtract that from the mean of your dependent variable, and then you've got the difference between your predictions versus that mean and what the actual mean was, so you can adjust it up like that, just like we did last class. Yes, we will have more than one slope.
No, when you make one in the slope, you just multiply the slope, like subtract it from that. So we have more than one slope. Which slope are we going to use?
We're going to use all of them. But we will multiply each slope by the mean for that dependent variable, plus the next slope times the mean for that dependent variable. Okay, so with our multiple regression equation, again, we can just write it like this, very simply. Y is equal to our predicted y's plus some error. We can change what the predicted scores are. So this is basically what you guys said before. So y, we have some slope for the first independent variable, plus some slope for the second independent variable times the second independent variable, plus some intercept and error. So each slope is the slope that's predicting the dependent variable from one of the independent variables. So this slope predicts this from that. This slope predicts this from that. And the second part, holding the others constant. So when we are making our predictions from this, it's like we're not thinking about anything else. We just want to make our best prediction for this based on this only. Okay, this has to do, this holding the other constant is related to these dots. So later, please remind me to talk about the dots again. If you can remember, talk about the dots. Okay, so imagine that we have our test 2 scores. In last class, we tried to predict test 2 scores from test 1 scores, right? But we have more data than just test 1 scores. We also have homework average scores, we have number of times that homework is submitted, lots of other variables that we could try to use to figure out what test 2 score someone we would predict to have if they had some other values for the other variables. So here are 3 correlations. We have the correlation between our test 2 and our test 1 scores, right? I said there would be multiple correlations. So here we have our dependent variable with one of our independent variables. Here's a correlation between test 2 scores and the average homework scores. This is a different correlation between our dependent variable and the other independent variable. And we have a correlation between our test 1 scores, that's this, and our homework scores. Right? These things could be correlated. They should be correlated, right? People who did more homework should probably have done better on test 1 too. On test 1 as well. Right? So, you do these correlations, and they're all significant. So, let's visualize these different relationships. We can start off with their scatter plots. This is the same scatter plot that we saw last class, right? So we have test 1 scores. As test 1 scores increase, generally there's an increase in test 2 scores, right? This is captured by a positive correlation. And if we square the correlation coefficient, what do we get? We get the coefficient of determination, which tells us what?
The amount of variance explained by the later.
Yeah, it tells us the percent of variance in test 2 scores that test 1 scores explain. So test 1 scores explain 45% of the variance in test 2 scores. Okay, now we don't have to use a scatter plot. Let's go back to Venn diagrams. Do you guys remember these at the very beginning of the semester? We talked about Venn diagrams. And we can have males and females. and then psychology majors, and sociology majors, and see the overlap. Basically, they told us something about how many of the females are psychology majors, or how many of the males are history majors, or whatever. So we can imagine we have our test 2 scores, right? And we can think about the test 2 scores, like the variance. If we want to standardize things, it makes things easier. The variance will just be 1, right? If we took the standard deviations of all of our test 2 scores, standard deviation of those transform scores would then be 1, and the variance would also be 1. Okay, so there are our test 2 scores. Circle represents variance. And we also have our test 1 scores, right? Now, there's a relationship between the test 1 and the test 2 scores. So 45% of these scores are explained by variations in our test 1 scores, right? Now, you're going to have to forgive me. So I'm trying to represent 45% here. I don't actually know like an easy way to create the Venn diagrams where the proportions will be perfect. So forgive me if the proportions are a bit off. Hopefully you'll get the idea. All right. So we have our test 2 scores, and about 45% of them are explained by test 1 scores, right? That's what this Venn diagram is telling us. Okay. So we just looked at test 1 and test 2 scores. We can also look at homework and test 2 scores. So here's the scatter plot for homework and test 2 scores. So these are the mean homework scores. So as the mean homework scores increase, you tend to have an increase in test 2 scores, right? The correlation here is a bit lower than it was before. So again, the coefficient of determination is also going to be lower. But the mean homework scores actually account for about 40% of the variance in our test 2 scores. It's still quite a bit. So we can go back to our Venn diagram. So we have our test 2 scores, and we can put our homework over them. And about 40% of the variance in our test 2 scores is accounted by the variations in our homework. Right? So that's homework in test 2. We can also look at homework in test 1. Right? So we talked about test 1 and test 2, homework in test 2. Now this is the last potential combination of 2 of those 3 things. So homework in test 1. And again we see a positive correlation. So as mean homework scores increase, test 1 scores also tend to increase. Right? This is weaker still than we had before. It's the weakest correlation that we have. So the coefficient of determination is less, but still it's about 30%. 30% of the variance in our test 1 scores we can explain with the variations in the homework. Now, homework should not be up yet. So when we just plotted the 2, we said like, okay, this represents the percent of variance in our test 2 scores that's explained by one of our dependent variables, right? Now, we could ask, in fact we are asking when we are doing a multiple regression or multiple correlation, we're asking basically how much do all of our dependent variables explain variance in our how much do all of our independent variables explain variance in our dependent variable, right? So we can plot all 3 of those things. So this is the variance in test 2 scores that's explained by test 1 scores. This is the variance in test 2 scores that's explained by homework variance. And you might be tempted. So before we found that this was about 45%, right? And this was about 40%. So you might want to say, okay, so these explain 85%. Just add them up, right? No, why not? There's overlap between the 2. Now, if these were completely independent, if these two things weren't correlated at all with one another, that would mean there would be no overlap here. Right? And if there was no overlap here, then we could say just add them up. Easy. Right? But there is overlap. So we're going to need to get rid of. We're going to need to get rid of this, right? Because when we account for it here and account for it here, we've accounted for this twice.
But we should add the bottom.
We should add this.
Only something.
No, subtract like only the part which is in the base side.
Just this. Yeah, just this. Because this was this. And this was this. So we need to get rid of this. Right? Good. Alright. There's another problem if we just did it like this. We would count all the variance of all of our dependent variables in the calculation. And this doesn't make a whole lot of sense here, so bear with me for a second and we'll get through it. So let's figure out how we need to do this. First, let's account for the relationship between our dependent variable and homework. So we've already figured this out. So the correlation between our test 2 scores and our homework, our average homework scores, if we square this, we get the percent. Actually, this should be 0.4, right? So I multiply by 100 to give us the percent. So that's giving us the percent of the relationship between the test 2 scores and our homework, right? The percent of variance in test 2 that's explained by homework. Now, what we want to do is find the unique relationship with test 1. If we go back to this Venn diagram here, that gives us this part, the first thing that we did. But what we want to do is we want to find the unique relationship between test 2 and our homework, right? Not any of the relationship that's not unique. These relationships are not unique. These relationships are explained by one another. So we want to get like the unique relationship. So, to do this, we don't want to get the variance accounted for by test 1. So what we want to do is we want to get the variance that's accounted for by the variations in test 1 that aren't linearly associated with homework. What? What? Can anyone explain that better than me?
Is it 1 minus r?
1 r squared.
1 minus r squared. There's going to be a 1 minus r squared involved. Indeed.
It's not determined.
So that's exactly right. We had r squared was the percent of variance that was determined by something else. And 1 minus r squared was the percent that's left over. That's unexplained. That's unique. Right? So we've already accounted for the variance in the homework. So we don't want to account for it twice. Right? So let's predict test 1 from homework. If we predict test 1 from homework, then we can break that variance up into pieces. The part of the variance that's explained by the relationship between test 1 and homework, and then the rest. The variance that isn't explained by homework. And we don't want the part that's explained by homework because we've already accounted for homework originally. It gave us the 45%. Or whatever it was. So we can do this. So slope is equal to the correlation of test 1 and the homework scores. Right? So this is the correlation between test 1 and homework times the standard deviation for test 1 divided by the standard deviation for our homework. Right? The standard deviation for the homework is in the denominator here because this is the one that we've already accounted for. This is the one that we're using to predict the test 1 scores from. Yeah?
We're taking the slope for 2 independent variables. But
yes.
Now we're just making the test 1 a dependent one.
Yes, that's exactly right. We are trying, ultimately, what we're trying to do is predict test 2 scores from homework and test 1 scores. Now, we started with our predictions of test 2 scores just from the homework. So we said, okay, we've got this variance accounted for. Now, we don't want to account for any of the variance in homework anymore, because we've got that part figured out. Okay? So we want to remove the homework variance from our test 1 variance, because they're related. We want to get rid of that part, because we've already accounted for it. Right? We don't want to account for it again. So what I am now doing is basically treating this second independent variable as a, did I say that right? Our second independent variable as a dependent variable. Okay, so we define the slope. Once we found the slope, we can calculate the intercept. Right? This is the same thing that we had last time. So the mean for our test 1 scores minus the mean for our homework average times the slope. That gives us the intercept. Now what we can do is we can estimate what the test 1 scores should be, given a linear relationship with the homework. So we have exactly the same form that we saw from last class. Thank you. Okay, so our estimated test 1 scores is just the slope that we found before times the homework scores plus the intercept. So now for each homework score that we have, we'll get a predicted score for our test 1, right? Now those predicted scores, those are related to homework. The variance there is completely related to the variance in homework, right? And we don't want the variance in homework because we've already accounted for it. So, what can we do? Remember how we found the errors? And we demonstrated that, like, if we sum them up and sum the squares, we would get the least squares. Anyway, we're going to use them a little bit differently today. So, we have the errors. This is the T1 scores, the test 1 scores that we actually have, minus our predictions. If you think back to that formula that we had before, we had something like our estimate of y is equal, y is equal to our estimate of y plus some error. So what we've basically done is we have solved for errors. So error equals y minus our estimate of y, right? Now, the errors, should they be correlated with our homework scores? No. They should be independent of our homework scores, right? Because we've already accounted for our homework scores with our estimate. The estimate is correlated with the homework scores, and we subtract out those estimates. So we're getting rid of them. So now, what can we do? Well, the errors, this leaves us the variations in test 1 that are not explained by the linear relationship with homework. So we can use this to figure out if the variance in test 2, which is the dependent variable that we are really interested in, is related to the unique variations in test 1, right? When we had just T1 by, when we had T1 by itself, this T1 includes variations that are associated with the homework and variations that aren't associated with the homework, right? So we got rid of the variations associated with the homework, and we were left with the variations that aren't associated with the homework. These are unique variations. So if we think back to the Venn diagram, what we have now is this. That part. It's a part of test 1 that is uniquely varied, right? Not variations that are explained by our homework, just the unique variations. Okay, so let's semi-partially predict test 2. I'll explain the language in there. So, I just correlated test 2 with the errors. So what am I doing here? I'm seeing if there's a linear relationship between the test 2 scores and the unique variations in test 1 that haven't been explained by anything else. Okay? So we do this, and boom, it's 0.388 jump. This is smaller than the previous correlation, right? The previous correlation was like 0.6 something. If we go all the way back. That one. Test 1 and test 2. So originally we had this, right? Right, the correlation between test 1 and test 2. What we just did was found the correlation between the unique variations in test 1 and test 2, right? So if this is the total correlation between test 1 and test 2, after we've accounted for some of those variations in test 1 with something else, we should have something that's smaller. And we did. All right. How? Okay, so this is just the correlation between test 2 and the part of test 1 that isn't linearly related to homework. This is known as a semi-partial correlation. Thus, the semi-partially predictor. A semi-partial correlation. Okay, so we have correlations. We have semi-partial correlations. We're going to have something else too. We'll get to that in a second. But first, let's talk about semi and partial and what those things mean. So what does it mean? Partial. Partially. So partial, you can define it a couple different ways. One is a noun, right? Partial. You get partial credit on your homework because you turn it in right? You don't get all of the credit for your homework, you get a part of it. You get a piece of it, right? Or the grade at least. So our first definition is just a part. The second one has to do with the verb. So what is partial in like a verb sense? To make something into parts, right? I have an orange. Who's hungry? I will partial the orange into pieces, right? I will divide the orange up and I will share it. So partial as a verb is like dividing something up or breaking something up. So we have done this before. We have broken things up before. Where have we broken things up? Quantiles break up distributions. So quantiles partial distributions into a part that is greater than something and a part that is less than something. Perfect. I wasn't even thinking about that, but you're absolutely right. Where else have we seen it?
Variance.
Variance. Variance. What do you mean variance? How have we partialed variance?
Effect and errors.
Yeah, we've taken these sums of squares, right? We get our total sums of squares. And then we chop it up into pieces. This piece is for that effect. This piece is for that effect. This is for the error. This is for the subjects. This is for the, right? We're basically taking some whole thing, breaking it up. Degrees of freedom we've broken up. We say, oh, we have 25 degrees of freedom total, but we have one way ANOVA, and it's non-repeated measures, and there are 3 levels, so we have to get rid of more degrees of freedom, right? So we break up the degrees of freedom. We have different degrees of freedom for our errors, and for our effects, and our interactions. Yeah, we've done this. We're good with partial. I hope. Okay, so we've divided up some of the squares, and what we just did was actually partial. We just partialed the variations in test 1 scores, right? We had total variations in test 1 scores, and then we found part of those variations that were related to homework 1, or the homework scores, and then another part that was uniquely associated with our test 1 scores. Okay. Okay. Alright, so semi, what does semi mean? Half? I did a Google search for semi today. Semi. Define semi. Half. Oh, that wasn't what I wanted. The next thing was a truck, a type of truck. That wasn't what I wanted either. Is there any other definition for semi? Semi can mean half. Step by step. Want to give me more?
Something related to part of.
Part of. Just stop there. Part of. Incomplete. Semi, you have part of something, right? Half is part of something. So, semi, incomplete, partial. So we could call this semi-partial correlation, we could call it a partial-partial correlation, but that's just really confusing, so we'll stick with semi-partial correlation. All right. Because semi-partial correlation isn't confusing at all, right? All right. So we partialed the variance in test 1 into pieces, right? We had the part of test 1 that was associated with homework, and we had the part of test 1 that wasn't associated with the homework. But we didn't partial the variance in our test 2 scores, right? We said, okay, we have all of our variations in test 2 scores. What percent of all of these variations are uniquely explained by the unique variations in this? So what we did, although we took out the homework from the test 1, we didn't take out the homework from the test 2, right? In fact, we left it in on purpose. We found the correlation and then the coefficient of determination for the homework in test 2, and then we added the unique correlation, the semi-partial correlation, and then we could square that to get like the semi-partial coefficient of determination that told us the unique variance in our test 2 scores that was explained by test 1. All right. So that was the part that contained the variations in test 1, and then T2 contained all of the variance in test 2. So by only taking out the variance in homework from one thing, we only partially partialed out the variance in homework. Does that make sense? So we took it out of one, we didn't take it out of the other. We only took it out of part of all of the variance. All right, so semi-partial correlation. So this is what we found, right? 0.388, that's what was like 2 slides ago. You can solve this directly. You don't have to go through all these steps. I like to go through the steps because then to me, like, it makes sense. Aha, let's predict our test 1 from our homework. Okay, now let's find out what's left over. And now let's see how this correlates. That makes sense to me. From looking at the formula by itself, it's not like incredibly obvious, at least to me, what's going on. Parts of it make sense. So the correlation between y and x1, so this would be like a correlation between test 2 and homework, minus the correlation of test 1 and test 2, times the correlation between test 1 and the homework, right? All of that divided by something, you mentioned the 1 minus r squared earlier, which was the variance that's left over. The variance that's left over from what? The variance that's left over between the relationship between, these are our 2 independent variables, test 1 and the homework. Test 1. Let's get this clear. Okay, so we have our IV, right? Our IV was test 2.
No, test 1.
dv was test 2. So this is y, right? Now, we had two independent variables, test 1 and homework. So these are both x's. Which one's the 1, which one's the 2? Well, we just found the semi-partial correlation coefficient for what? Test 1, right? So here, this is the semi-partial correlation coefficient for x1. So let's say test 1, that's our x1. And then homework, this is x2. If you wanted to find the other semi-partial correlation coefficient, you just swap them around. So this would become 2, this would be 2, this would be 1, this would be 2, 1, 2, 1. Actually, these, those are the same regardless of which one you have first. But those other things will change. Okay, so if we look at this, our semi-partial correlation coefficient for test 2, I'll just say T2 and T1, T2, T1, T2, homework, T1, homework, T1, homework. So this is the correlation, just the raw correlation between test 2 and test 1, right? But we are taking out of that variations in test 1 that are explained by test 2.
Where does the correlation of T2 and error falls in this?
So the T2 is just regular old T2. But the error is actually something different. So the error...
Sorry, what does this explain? The equation?
This equation allows you to compute this without estimating what T1 should be based off of the homework scores, and then figuring out what the errors are. So this allows you to solve for this directly without going through those 5 steps. So notice that in here, all we have are the correlation coefficients, right? And we had all of these things in that first step. On like that first slide, I had the 3 correlations. So rather than going through all of those steps, which are fairly time-consuming and you can make mistakes fairly easily, you don't have to go through all of that. So this relationship here is captured by this, but this doesn't have any expression of the errors in it directly. But all of these algebraic manipulations need up to give us that. You will get exactly the same thing.
Can you show this in Venn diagram?
Can I show you this in a Venn diagram? Yes. Okay, so this is our test 2. This is homework. This is test 1.
Can you switch it?
I'm going to get a mustache again. But so, you like this better?
Yes.
Okay. Is that what I started with?
Yes.
Okay. So what this tells us, so this is test 2 and test 1, right? So this is this.
This small part.
It's telling us this as a proportion of that if we square it. The percent that's explained by the unique relationship, I'm sorry, not this part, not that part. The part of T2, so this is all of the T2, that is uniquely explained by T1. That's that. Okay? All right. There's the R code for it. And it works. Unless I made a copy-paste error somewhere. But that, it should work for you. All right. Now, so we found the semi-partial correlation coefficient. We can find the variance in test 2 uniquely accounted for by test 1 just by squaring the data. Square it, boom, we're done. You see this represented like this, SR squared. So we have the semi-partial and the partial. So this is test 2, test 1, homework, test 2, test 1, homework. So with the semi-partial, what we were doing, we were finding this piece relative to everything in our test 2 scores. We only partialed out homework from T1. Here, with the partial, not the partial or the semi-partial, with the full partial, we're going to pull out homework from everything. So basically, it's like getting rid of all of that. These are the remaining variations that we have in our test 2 after we pull out the relationship, after we partial out the relationship with our homework. And this is the variance in test 1 after we've pulled out the relationship between homework. And this, which is exactly the same as that, is now compared not to the whole thing, but only to that. It's only compared to the part of our dependent variable that isn't associated with any of the other variables. So, if we square this, will tell us how much of the variations, or percent of the variance in our dependent variable that aren't explained by other variables is explained by the variations in the independent variable for which we've calculated the partial correlation. It's not related to other variables. So the partial correlation, here is a way that we can figure this out. So I'm calculating a slope for our test 1 scores from our homework. I'm going to partial the homework from our test 1 scores. This is exactly what I did before. I just, instead of naming it slope, I named it T1 slope to make it clear what I'm doing a bit later. So find the slope, we multiply the correlation by the appropriate standard deviations, right? So that gives us the slope of the relationship that's describing relationship between test 1 and homework. Okay? So if I was going to do a simple linear regression for test 1 from the homework, which is what we did earlier, then we find the intercept. We get the mean of test 1 minus the mean of the homework times the slope. Then we can get our estimates for our test 1 scores, which we already did. And we can get our errors, which we did before. And before we correlated these errors with test 2, right? But now, for the partial, we're not correlating with it with all of test 2. We're only correlating it with the part of test 2 that's left over after you've explained what you could with the other independent variables. In this case, we only have 1. So we'll have a test 2 slope, right? So the test 2 slope is the correlation between test 2 and our homework. Right? We're partialing homework out of everything. So we're predicting test 1. We're also going to predict test 2. So correlation of test 2 and our homework average times the appropriate standard deviations. Okay, then we find our intercept, the mean of test 2 minus the mean of our homework times the test 2 slope. We find our estimates of test 2. That's just the slope times each homework score plus the intercept. And we have our errors. The errors here, these T2 errors, these are the errors in prediction of the relationship between test 2 and homework. So the errors is what's left over. The variance in our test 2 after we've already pulled out all of the variance associated with the homework. Okay? So now what can we do? Now we can correlate these two errors. Calculate what's left of our test 1. Right? That was this, we're going to correlate this with that. Right? So we do it. And we get 0.503. You guys notice the difference between this and what we had earlier? So, the semi-partial correlation. Does anyone remember what that was?
It was test 2 and
It's like I think it was like 0.38
3.
or something. Let's find it. 0.38. 0.38. Or 0.39 if you round out. And what is this? 0.50. It's bigger. Why is it bigger?
Because the ratio of this, the overlapping considered with the whole
Yeah.
is bigger with this than considered with the only errors.
So before we were comparing like this piece to everything. Now we're comparing that piece to not everything. Right? So out of the stuff that's not explained by the homework, this explains what percent? It's not 50%. This is just the partial correlation coefficient. So we need to square it. So it will be about 25%, right? What? Copy paste. Sorry. 25, whatever. You can also solve this directly with this. Another fine formula where we only have the correlation coefficients that we had originally. So you don't have to go through all of those steps to find it. And should be 0.5. I'm going to have to check this. This worries me that I have that there with the wrong answer. This should be correct. Actually, we can check if it's correct. So the correlation of T2, T1, that's this. Correlation of T2 homework, okay. Correlation of T1 in homework, that's that. Correlate square root of all of that. So square root of 1 minus the correlation of T2 in the homework squared times the square root of 1 minus, okay, so this is right. So this should give us 0.5. Okay, so now we've done all of this. For what? Well, so we can figure out what the best equation is. The best equation. The linear equation. The estimated y equals some slope times some independent variable plus another slope times the other independent variable plus whatever other slopes and independent variables we have plus some intercept. Right? So we found the slopes by multiplying the correlation between the variables by their standard deviations. Here it's going to be a little different. So typically for multiple variables, you're going to multiply the partial correlation for each variable by the standard deviations of the variations in our variables that aren't explained by the linear relationships with the other variables. So we're going to multiply that piece that told us something about the percent of variance in what's left over in our dependent variable is explained by this independent variable uniquely. We're going to multiply that by the variance or the variations in both of those that have had everything else pulled out of it. Everything else has been partial from it. So we'll have something like this. Our slope for T1, that would be D for T1, is equal to our partial correlation coefficient for T1 times the standard deviation of our T2 errors. This is what's left over from our predictions of test 2 by homework, divided by the standard deviation in our test 1 errors. That is what's left over in our test 1 after we've pulled out the variance related to homework. So this all has to do with partial, fully partial. We can solve this directly. Yay. There it is. And we get 0.47432124. So the slope. Now we have something that we can say. This was for test 1. So the test 1 slope. So as someone has a test 1 score that increases by 1 point, how much, on average, should their test 2 score increase? 0.47. So each point increase on test 1 is associated, uniquely associated with an increase of about half of a point, right? On test 2. Cool. Now this is just for one of the multiple regression coefficients. We also need to do this for the other one. Huh? What did you say, homework? That's a brilliant idea. You guys can do that for homework. I like that idea. I wish I had thought of that before. Anyway, notice I'm not talking about it up here. You guys can do this. All you have to do is figure out the correlations and the standard deviations. And you guys know how to do this, right? SD, some variable. SD, some other variable. Correlation between two. Correlation T1, T2, correlation whatever. You can do that. You know how to get all of these pieces. You have the formulas. You can compute them.
The thing is that if we found partial for T1 and partial for homework, there is in the middle is going to be left.
Yeah. There's something that's left. So if you find the partial for the homework and the partial for the T1, what you've ended up finding, if I draw this bigger, T1, T2, homework. So you find this, you find this, in the middle there's something else. What is that? Does anyone know? Do I have 5 letters today? I might have 5 letters today. I have 5 letters today. Who wants to earn 5 letters? What is this? So this is the unique relationship between T2 and T1. This is the unique relationship basically between T2 and homework. What is this?
The ununique relationship between T2 and the both.
Once we have the partial regression coefficients, we can make our predictions for the average values of our IVs and find the difference between those predictions and the mean for our dependent variable. Right, so we had that part of the equation, the slope, the slope for the unique relationship between test 2 and test 1 times the test 1 average score plus the slope that describes the unique relationship between homework and test 2 times the average homework score. Subtract that from the mean of the dependent variable, which is test 2, and boom, you got your intercept. Alright. Next class we will talk more about multiple regression and correlation. This class was difficult.
Yes, it was.
On Friday, we will see how we can skip a lot of this stuff and just be able to calculate the things that we're interested in directly.
Good.
But it's important for you to understand sort of how these things are working. Because without understanding how they're working, like, you really can't be sure that you're doing the right thing. So now, you at least have the information about how the things are working. So you can try to understand that. Come and ask me for help. Do some homework. And then we'll see the easy way on Friday.